Okay, so let's have another example for the area moment method. Okay, for example, we have this beam loaded as shown. We assume that the EI is constant and required. Okay, letter A, the rotation at A. Then letter B, the maximum deflection. Okay, so to start our solution, we need to first to compute for the support reactions. So we may do, this is the summation of moments at A is equal to 0, assuming clockwise moments to be positive. So that is, okay, the resultant of this uniformly distributed load is 32 kilonewtons, and it is acting at a distance of midway of the uniformly distributed load, that is at a distance of 2 meters from B. So we have that as 32 multiplied by, that is 4 plus 2, we have 6, minus the reaction at B, this is multiplied by 8 equal to 0. So we have the reaction at B is equal to, we have that as 32 multiplied by 6 to be divided by the span of the beam, that is 8 meters. So we have this one as 24 kilo newtons. Then the reaction at A, and this is by summation of forces vertical equal to 0, assuming upward forces to be positive. So we have that R sub A plus R sub B is 24 minus the downward load 32 kilonewtons equal to 0. So 24 minus 32 is negative 8 transpose. We have the reaction at A is equal to 8 kilo newtons. So we have now the support reactions. So we have R sub A is equal to 8 kilonewtons and R sub B is equal to 24 kilonewtons. So after computing for the support reactions, so we are to decide on what point we are going to do the moments for the moment diagram. So since we have our uniform load is on the right half of the beam, it is more convenient for this case to do the moments at B, or that is on the right end. So that is 8. We have the 8 multiplied by the span. So 8 times 8, that will give us a positive 64. So starting from A, so 8 times 8 towards B, that is 64 kilonewton meter. So this is positive 64 if we are to consider our values above the axis to be positive. Then for the uniformly distributed load, take note that this is for the load diagram. On our load diagram, the degree of the load is, let's say, N. Then, if we are to proceed on the moment diagram, the degree of the diagram will be, that is N plus 2. Okay, so what will be the magnitude of that moment? That is the same as we have 8 times 4. 8 times 4, that is 32 at a distance of 2 meters. And its direction is towards below the axis, or the horizontal axis for our moment diagram. So we assume that to be negative. So again, since the degree of our load diagram is N, so we add 2 as we go down to our moment diagram. So for a uniformly distributed load, obviously, the degree of a uniformly distributed load is, the degree is equal to 0. So that is, the degree of our moment diagram caused by this uniformly distributed load will be a second degree. So if it is a second degree, it will be a curve graph. And let's say this is, we have negative 64. And the degree of this curve is equal to a second degree, since the degree of our moment diagram is 0. So again, if we are to recall, how do we locate the centroids of this spandrel? That is 1 over the degree of the curve, plus 2 multiplied by the base. How do we compute for the area of spandrels? So the area is equal to, this is 1 over n plus 1, the base times the height. So just to recall this formula for this spandrel. Okay, so we may now proceed to our solution. Okay, to imagine the deflection of the beam, we may draw the elastic curve, or that is the deflected form of the beam. So let's say this is the deflected form of the beam. Alright, then first requirement, the first requirement is the rotation at A. So take note, if we are measuring rotation at supports, so usually our reference is the horizontal. So let's say this is the rotation at A. So initially, for example, for the beam, we don't have a load, so we assume that the beam will be horizontal. So the rotation of this elastic curve or the deflected form of the beam is, let's say this is the theta A. How do we compute for that value? So we may draw a tangent line at A towards B. So we are to draw a tangent line at A that will represent the slope. So let's say this is the tangent line that intersect the elastic curve at point A. So we are to consider this distance from point B of the beam towards the tangent line. This vertical distance is the deviation from our initial point, or wherein we have the tangent line, that is the deviation from A towards the second point, or the second reference point, that is B. So we read this one as the deviation from A to B. How do we compute for that value? How do we compute for that deviation? So we have the deviation from A to B is basically equal to the area of the moment diagram. So this is the area of the moment diagram. This is to be multiplied by the distance of their centroids with respect to point B. So our clue is our second point, that is point B, that will be a reference point for the distance of the centroid of the moment diagram. And this is to be all over divided by EI. So how do we compute now for the deviation from A to B? So all we have to do is locate the centroids of these diagrams with respect to point B. So for a triangle, we know this distance. Let's say the bar x1 is equal to 1/3 of the base. Then for this spandrel, this distance is, that is the bar x, its equivalent bar x2 is equal to, that is 1 over the degree plus 2 of the base. Okay, so computing for, excuse me, computing for the deviation, this is the deviation from A to B is now equal to, what is our first area? That is the positive area. That is, we have 1/2. The base is 8 meters, so this is for the triangle. The height is 64. The distance of its centroid towards point B, that is 1/3. What is the base of the triangle? That is the same as the length of the beam. That is 8 meters. Then plus, for the spandrel, that is, we have 1. What is the area of the spandrel? What is 1 over n plus 1? The degree of the spandrel is 2 plus 1. What is the base of the spandrel? The base of the spandrel is 4 meters. What is the height? That is equal to negative 64. Its centroid towards point B, that is 1 over its degree 2, plus 2. This is multiplied by the base. What is the base of the spandrel? That is equal to 4 meters. So we can have now the deviation. This is the deviation from A to, the deviation from A to B. Computing for this value. So we have that as, we have 0.5. We have 0.5 or 1/2 of 8. This is multiplied by 64. Then multiplied by 1/3 of 8, or that is simply 8 over 3. Then plus, that is 1 over 2 plus 1 is 3. Then multiplied by 4. The height is negative 64. Then the centroid is, that is the same as 4 over 2 plus 2, or is 4 over 4, or simply equal to 1. So we have the deviation. Supposedly, the right side of the equation should be all over EI. So we have the deviation is equal to 1,792 over 3. This is 1,792 over 3, or it's the same as over 3 EI. So this is the deviation from point A to point B. So how do we compute for the rotation at A? If you are to consider this two angles, or this is theta A. If you are to consider the rotation of the beam due to the deflection, this is the same as theta A. So we call this two angles are the vertical angles. We call them the vertical angles. For example, we have two lines intersecting each other. If this is theta A, this is the same as theta A. How do we compute for theta A? It's like we have this triangle. All we have to do is consider that triangle, the length of the beam. So we have the length of the beam is equal to 3 meters, and this is the deviation from A to B. How do we compute for this angle? This is the same as the angle theta sub A. So we can use tangent. That is the tangent of theta A is equal to opposite. That is the opposite value. We have the deviation from A to B divided by the length of the beam. But for the cases that we have a very small value of theta A, let's say for the theta A is a very small value, take note that for a small value of an angle, that is the tangent of theta A is simply equal to the theta A. Alright? So you can check that using your calculator or trial some values of small angles. That is simply equal to the deviation from A to B divided by the length of the beam. So computing for the first requirement, that is letter A, we have the theta sub A is equal to opposite. What is the deviation from A to B? We have that as 1,792 divided by 3 EI. This is divided by the length of the beam. The length of the beam is equal to 8 meters. So we have now the rotation of theta A is equal to, we have that as 1,792 divided by 3, then again divided by 8. So we have that as 224 divided by, in terms of EI. So this is 3 EI. 224 over 3 EI. So this is the rotation at A. If we are to consider the unit, this is the same as kilonewton meter squared. For the second requirement, how do we compute for the maximum deflection? So first thing to do, we are to assume the location of the maximum deflection. For this case, as you can see, our load is on the right half of the beam. So I'll be assuming that the maximum deflection is more likely after 4 meters from point A. More likely the maximum deflection is here. Let's say this is the Y max. So take note that the tangent line or the slope of the maximum the slope of this elastic curve at the maximum deflection is horizontal. That is, if we are to draw, for example, if we are to draw a horizontal line that will intersect the point of the elastic curve, that is the point of the maximum deflection. Okay? Then, if we are to observe this tangent line, this is the tangent line passing through point A. Okay, then our reference, how do we measure theta A is the horizontal beam. That is the same as we have two horizontal lines, for example, two horizontal lines that is intersects by a transverse line. So this is the same as theta A, and the angle on the other line is the same as theta sub A. So therefore, if we are to consider this angle, let's say if you are considering now this angle that is tangent at the point wherein we have the maximum deflection, this is the same as the rotation at A. Okay, so we have the same angle as rotation at A, considering these two tangent lines. So therefore, let's say this point, as the location of the maximum deflection will be point C. So that is theta sub A. The rotation at A is the same as the rotation, if you are to consider the tangent lines, that is from point C to point A. So these two angles will be equal. Okay, how do we compute for that location? So let's say we locate point C at a distance of, let's say at a distance of x from point A. And on the moment diagram, so we are to name these points on the moment diagram. That is at a distance of x from point A. So what will be the magnitude of the moment? So let's say this point will be, the magnitude of the moment at that point will be the moment number 1. So what is the magnitude of that moment, the moment number 1? So we have the magnitude of that moment, let's say moment number 1 is simply equal to, that is the support reaction at A, that is 8 kilonewtons a while ago, that is 8 times x. Then what about, let's say on this point, so what is this distance? So let's say this is moment number 2, that is on the spandrel. So if this is a distance x, if we have this distance as distance x, basically this distance is the distance x minus 4. So what will be the magnitude of that moment on that point, considering the 8 kilonewtons per meter load? So the magnitude of the moment at that point, let's say moment number 2, that is the same as 8. Its lever arm will be x minus 4. This is the resultant. 8 kilonewton meter times x minus 4. Then the lever arm is x minus 4 divided by 2. Or simply, our moment number 2 is equal to 4 or multiplied by x minus 4 squared. Okay? So how do we now compute for the value of x? Okay, so we have the rotation at A is simply equal to the rotation from point C to point A. That is equal to the area of the moment diagram. The area of the moment diagram from this is from point C to point A. So all we have to do is compute for the value of x. So this is divided by EI. So a while ago, what is the rotation at A? The rotation at A is equal to 224 over 3EI. So we have this value as 224 divided by 3EI is equal to, what is the area of the moment diagram from point C to point A? So we have a moment number 1, this is equal to 8 times x. Then a moment number 2, the moment number 2 is equal to, that is 4 times x minus 4 squared. So all we have to do is compute for those areas. So for the triangle, that is 1/2. What is the base? The base is x. What is the height? That is 8 times x. Then this is plus. For the spandrel, that is 1. I divide by the degree is 2 plus 1. The base is x minus 4. What is the height? The height is the magnitude of the moment. Okay, what is the magnitude of the moment? Okay, the magnitude of the moment is 4 times x, okay, minus 4 squared. Okay, supposedly this is, since that is below our horizontal axis, supposedly this is negative. So this is negative 4 times x minus 4 squared. Okay, so simplifying, the right side of the equation will be all over. This is all over EI. So we may cancel the EI. So this is the same as 224. We have now 224. This is divided by 3 equal to, what is 8x over times 1/2 of x. We have 4x squared. Then this is minus, that's minus 4. Okay, 2 plus 1 is 3. X minus 4 times x minus 4 squared is the x, minus 4. This is x minus 4 cubed. Computing for the value of x. That is the location of the maximum deflection. So we have that as 224. This is divided by 3. Is now equal to, this 4 alpha x. This is squared. Minus, we have the 4 over 3. This is multiplied by the alpha x. Minus 4. This is raised to 3. So shift solve. So before we press equals, the assumed value of x is near the value of 5 or near the value of 4. So let's say press 4, then press equals. We have a syntax error here. Shift solve 4. So we have the location of the maximum deflection is at a distance of 4.322 meters. So the assumption is correct. It is more than half. More than half of the length of the beam. Now, if we are to observe this tangent line, for us to compute for the maximum deflection, if you are to consider this tangent line, that is the tangent line intersecting point C. This is the tangent line intersecting point C and, let's say, the horizontal axis of the beam. How do we describe this distance? This distance is the same as the maximum deflection. From the horizontal axis of the beam to point C, that is thus the same as the y max. If we are to compute for its equivalent deviation, that is the same as the deviation. What is our initial point, or the point wherein we have an intersection of the tangent and the elastic curve? That is the same as the deviation from point C. Then our reference point will be point A. So the deviation from point C to point A is simply equal to the maximum deflection. Okay? So we are now to compute for the equivalence of the moment so that we can place their value. So we have moment number 1 a while ago. Moment number 1 is 8 times x. So this is the same as 8, the value of x. The value of x is equal to 4.322. What is this value? So we have 8 times 4.322. Is 34 we have 34.576 kilonewton meter. Then we have moment number 2, supposedly this is negative 4 multiplied by x, that is 4.322, and then minus 4 squared. So we have that value equal to, we have a negative 4 multiplied by 4.322 minus 4 squared. That is negative 0.415 kilonewton meter. So if we are to place these values in our moment diagrams, so moment number 1 is, we have this as 34.576, and moment number 2, we have moment number 2 is equal to 0.415 kilonewton meter. And this is supposedly negative. So all we have to do is I compute the equivalent of the deviation from point C to point A. That will be the same as the maximum deflection. So by the way, what is the distances, or what are the distances? We have the value of x is equal to, that will be the base of the triangle, 4.322, and this one is x minus 4. That is 4.322 minus 4. The base of the spandrel will be, this is for the base of the spandrel, 0.322 meter. Okay, so those are the distances or the bases of the triangle and the spandrel. I'm computing now for letter B, the second requirement. All we have to do is I base this one on this portion of the moment diagram. All we have to do is consider these areas within the span of x is equal to 4.322 meters. So we have so this is the deviation from our first point, that is point C to point A, is equal to the area of the moment diagram. Then this is to be multiplied by the x multiplied by to the distance of their centroid towards point A. Take note, this time the centroid is towards our second point, towards point A. And then this is, this term should be divided by EI. Okay, so we are now computing for the deviation from A to C. So we have the deviation from C to A, sorry. From C to A is now equal to, for the triangle, that is, we have 1/2. For the triangle, is 1/2. What is our base? That is 4.322 meters. Then its height is equal to 34.576. And the distance of its centroid will be 2/3. Take note that is the centroid should be with respect to point A this time. This is our bar x this time. So 2/3 of 4.322 meters. Then plus for the spandrel, that is 1. The degree is 2, plus 1. What is the base of the spandrel? The base of the spandrel is 0.322. The height is negative 0.415 kilonewton meter. The distance of its centroid, by the way, what will be the distance of this centroid towards point A? The distance of its centroid, the distance of this centroid towards point A, that is the same as, we know this distance as 4 meters. So the equivalent bar x will be equal to, that is the same as, we have, that is 4 plus, that is the same as 3/4, 3/4 of 3 points of 0.322 meter. So why 3/4? Just to clear that part. Okay, for a spandrel, which is a second degree, okay, for a spandrel with a degree, second degree, if this is the bar x is equal to 1/2 plus 2 of the base, that is the same as 1/4, which means this remaining distance is the same as, if this is 1/4, the remaining distance is 3/4. Okay, so I hope that is clear. So for the spandrel, that is 1/2 plus 1, 0.322, negative 0.415. That is the distance of its centroid towards point A, that is 4 meters plus the 3/4 of 0.322 meter. So this will be the equivalent of the deviation from Okay, the deviation from C to A. That is the same as the maximum deflection. So I keep on forgetting that this should be divided by EI. So we have the maximum deflections now equal to, for the triangle, it is 0.5 of the base of 4.322. This is multiplied by 34.576. Then the distance of the centroid towards point A is 2/3 of 4.322. Okay, then plus, there is a 1/3 of the base of the spandrel is 0.322. Then the height is negative 0.415. The distance of its centroid will be 4 meters, okay, plus the 3/4 of the 0.322. And we have this value, the Y max, this is 215.101. Let's say 215.101, okay, this is in terms of kilonewton meter cube. And this is divided by EI. So this will be our answer for the maximum deflection. So that is the deviation from point C to point A, based on this figure. That is simply the deviation from point C to point A. So that's how we compute the maximum deflection. So draw a tangent line at the point wherein we have the Y max. Then we compute for the deviation from that point to the support. So that height will be the same as the maximum deflection. So this will be our solution for this example.